Hello everyone. So in the last discussion we talked about quasi-static process. We came to know that how a thermodynamic process undergoes, and it undergoes via quasi-static manner only, right? Today we are going to discuss when my system goes under a quasi-static manner, then what is the work done by my system, right? So when my system is going under quasi-static manner or very slow manner, then what is my work done by the system, right? So this work done by the system is also called as boundary displacement work or PdV work, right? So let us start the discussion how this derivation comes, right? But before that, let's have a quick recap from the previous discussion. So here we have taken the piston cylinder arrangement, and here the gas pressure force is balancing the all the weight over the piston top, right, as well as atmospheric pressure force. So currently my system is in thermodynamic equilibrium, right? So here this is the mechanical equilibrium expression, right? Gas pressure force is balancing the weight as well as the atmospheric pressure force, right? Now what we did we just remove one slice or one grain from the total weight, right? So if I remove this one slice of the weight which is having very less weight, let us call it dw, and this is tending to 0, right? So out of the total weight we have removed a very small weight dw which is tending to 0. So what will happen? There will be a small imbalance of forces on the piston, right? Now this w will reduce, because we have removed dw of weight. So now what will happen? The piston will go up. The piston will go up, or you can say the gas will expand, right? When gas will expand, there will be a slight drop in pressure and a slight increase in volume, right? Because small imbalance has been created. So piston will move up by dx amount, right? Dx displacement will be there. Now what will happen? Again equilibrium will be established. Again thermal equilibrium will be established, and the rest of the weight that is w dash is balancing this gas pressure force, right? Atmospheric pressure force, weight of the load, and the gas pressure force. So here this is the mechanical equilibrium condition. Under this thermodynamic equilibrium condition, this is my mechanical equilibrium condition, right? Again we'll do the same thing. We'll remove this again one slice of weight which is having very low value dw, right? Which is tending to 0, Again you can see this w dash will decrease, right? Because we have removed one small weight, right? Now what will happen? Again there will be expansion. Gas will expand slightly dx amount, right? So what will happen? The pressure will drop slightly, and volume will increase slightly. So this is here you get again a new thermodynamic equilibrium condition, or a new properties which established over here, P2 and V2. And again gas pressure force is balancing the total weight over the piston and the atmospheric pressure force. Like this we'll continue removing one by one all these small weights, right? When you remove all the weights, what will happen? Now only the atmospheric pressure force is acting on the top of the piston, and here only the gas pressure force is there, and these two will balance each other, right? So atmospheric pressure force and gas pressure force is balance each other, right? So what is happening? At every instant you can see there is a thermodynamic equilibrium establishing, right? And this is the mechanical equilibrium condition, right? So at this instant this gas pressure force is balancing total resistance force over the top of the piston. At this instant gas pressure force is balancing total resistance force on the top of the piston. Same goes here also, right? So this is the main idea behind quasi-static manner, right? At any instant my system is in equilibrium with the surrounding, right? So here my system is balancing all the resistance force at each instant of time, right? Now we come to calculate the work done by my system in moving upwards, or you can say moving upward in this direction, right? So let us calculate a small amount of work, right? Okay. So let's say this is a differential weight or differential work done. I'm calculating differential work done, right? So that is equal to F resistance into dx, right? This is a differential work done by my system in lifting these total weights, right? Now, this is a very general expression. It is valid for quasi-static process as well as non-quasi-static process both, right? But I want my process to be quasi-static. Now what condition I should put over here? Very simple. At every instant, my gas pressure force should balance all the resistance force over the piston. So if I generalize this discussion, let's say this is my piston, this is my piston. At any instant, let's say this is a gas pressure force. This is a gas pressure force. This is a gas pressure force, P into A, P into A. Right? And over the top of the piston, there can be any resistance force. There can be any resistance force. Right? There can be any resistance force. Right? Let's say it be an external weight W. Right? It can be atmospheric pressure force. It can be weight of the piston also. Here we have neglected the weight of the piston because we are assuming massless. It can be the weight of the piston also. Or you can assume there is a spring. There is a spring attached to the piston. Right? And when the piston is moving upward, the spring is getting compressed. So spring will also apply a downward force on the piston, right? So external force can be of many types, right? It can be external weight, right? It can be external weight, or it can be atmospheric pressure force, or it can be spring force, right? It can be weight of the piston, right? So many resistance force can be there over the top of the piston. But the key idea is that for a quasi-static manner, at every instant, this gas pressure force should balance all such forces, right? At every instant, right? So if my process has to be quasi-static, I have to ensure that this resistance, this F resistance is equal to gas pressure force, right? And from where? From initial to final state. From initial to final state throughout, this gas pressure force should balance the resistance force, right? When I do this, as soon as I write F resistance is equal to PA, I am declaring or I am ensuring this is quasi-static process. This is quasi-static process, right? So if I solve this further, this A into dx is nothing but a small increment in the volume, a differential increment in the volume, right? So this is dV, and this is pressure. So this is dV, this is P, and you are integrating initial to final condition. Right? This will give you total work done from initial to final state. Total work done from initial to final state. From initial to final state. Right? So this is a quasi-static work done. Right? This is what we call as PdV work, or boundary displacement work. Now to solve this, we should know P as a function of P, right? Otherwise we cannot solve, right? So P as a function of V, we should know somehow that will be given by some any property relation, right? P as a function of V, we should know, then only we can solve this integration. Right? So this is the expression to calculate the boundary displacement work, right? Undergoing quasi-static manner. Now there is a graphical interpretation of this expression. Let's try to understand. Let's say I'm taking pressure volume axis, right? Right? And I'm taking any curve, arbitrary curve, right? In this property diagram, this is my initial state and this is my final state, right? Now I take dV amount of thickness here on the volume axis, right? So let's say this is my dV amount of thickness here. dV is tending to 0. You cannot see from a naked eyes this much, right, gap, right, this much width, right? But to appreciate, I have to show some significant width, right? So this is dV, and let's say in this dV the pressure is P. The pressure is P, right? Pressure is P, right? So P into dV, this P into dV is a area of this very small strip, right? Infinitesimally small strip. Its area is P into dV. Now this area we will add up, because PdV we are adding up, we are integrating from initial to final state. So initial to final state, this area of this strip will add up, right? So when we'll add up all this infinite number of strip from initial to final state, so we'll get the total area under this curve, right? So total area under this curve you will get when you integrate or you add this PdV from initial to final state. So this is a graphical interpretation of this PdV work done, right? So if you want to know the area, right, or if you want to know this work done, so you have to see pressure and volume axis, right? Under the pressure volume axis, there will be a curve, right? So area under the PV curve projected on volume axis will give me quasi-static work transfer, right? Or boundary displacement work, or PdV work. Right? So this is a simple expression, but it has lot of implication in a coming lot of processes. So one thing very important you have to notice, that PdV is ensuring that this is quasi-static process, because we have equated resistance force to this gas pressure force from initial to final state. So I hope you have understood about this quasi-static work transfer. We'll see in the next video. I hope you have enjoyed it. Thank you.